The Manhattan Project is often reduced to a famous equation, E equals mc squared. But an equation did not build the first atomic weapons. The decisive challenge was geometric. How do you make many separate actions, distributed through space, arrive at one center with extraordinary coordination? This is a story about symmetry, secrecy, computation, and the terrible power of making an abstract idea physically exact. It is also the story of a crude drawing, recovered from an espionage trial, that unexpectedly resembles the opening move of a very different mathematical program. During the Second World War, the Manhattan Project became a hidden scientific civilization. Oak Ridge worked to enrich uranium. Hanford produced plutonium. Los Alamos became the secret laboratory where physicists, chemists, engineers, machinists, military personnel, technicians, and human computers attempted to transform nuclear theory into working devices. The project was geographically distributed, but every part of it was being forced toward a single objective. It was already a kind of network. Different sites, different languages, and different local problems, all connected by one global constraint. At the conceptual heart of the project was the chain reaction. One fission event could release particles capable of producing additional events. If each generation produced more successful interactions than the last, the process could grow rapidly. N sub k equals n0 times nu to the power k. But this elementary branching picture concealed an unforgiving physical problem. The material had to enter the required configuration before the reaction disrupted the configuration itself. The mathematics was not simply about releasing energy. It was about controlling space and time long enough for a collective process to occur. Two broad geometric strategies emerged. One assembled separated material along a line. The other attempted to compress material inward from many directions. The linear method was comparatively easier to reason about, but the plutonium produced at Hanford presented a problem. Its spontaneous fission behavior made the slower linear approach unsuitable. The plutonium design would therefore depend on implosion. That decision changed the Manhattan Project from a problem of assembly into a problem of symmetry. Early experiments struggled to create shock waves with the required coordination. Los Alamos concentrated enormous resources on making that inward geometry work. We can describe the essential difficulty using the language of harmonic analysis. Imagine the moving surface written as a spherical average, plus distortion modes. The term r of t represents ideal radial motion. The higher modes measure departures from symmetry. One region arriving too early, another too late, one direction receiving more force than another. The engineering goal was not merely to create a powerful explosion. It was to suppress the unwanted modes. Inward motion had to become almost independent of direction. A physical object was therefore being designed as a machine for eliminating asymmetry. No single mind solved this problem. Theory predicted possible behavior. Experiments exposed failures. Machinists translated drawings into matter. Instruments measured whether the waves were actually approaching symmetry. Every stage passed information to another stage. The project succeeded through repeated correction. Model, experiment, error, revised model. This is one of the deepest lessons of the Manhattan Project. A powerful theoretical idea means very little until every interface agrees. Equations, materials, tolerances, instruments, and human organization. The center could only be reached because an enormous distributed system learned to coordinate itself. Among the workers at Los Alamos was David Greenglass, an Army machinist associated with work on molds connected to the explosive lens program. Greenglass also passed information from Los Alamos into a Soviet espionage network. Years later, during the Rosenberg trial, he reconstructed sketches representing information he claimed to have transmitted. His testimony became part of one of the most controversial trials of the early Cold War. Later disclosures made important parts of that testimony deeply contested. What survives is therefore not a transparent window into Los Alamos. It is something stranger, a technical memory transformed into courtroom evidence, political symbol, and historical artifact. This is the Greenglass lens mold sketch, not a complete engineering drawing, not a blueprint from which a device could be reconstructed, a rough courtroom representation of a shape connected to an extraordinarily consequential geometry. Look past the handwriting for a moment. 4 regions bend inward. Outer structure is organized around an absent center. The drawing appears almost simple, but its meaning lies in what the surrounding geometry is supposed to make happen, at the point we cannot see. Now perform a mathematical act. Do not treat the drawing as a finished object. Treat it as a seed. Rotate it. Reflect it. Allow its copies to interact. Replace one planar silhouette with an orbit of related configurations. A 2-dimensional trace begins generating a 3-dimensional world. The center is no longer merely surrounded. It becomes a junction through which many geometric relations must pass. Here the historical image passes into the language of my Zeta-Space program. This is not a claim that the Manhattan Project secretly discovered Zeta space. It is a structural analogy. In the seed S3, the geometry is distributed across orbifold sheets, a seam graph, and a symmetry action. The surrounding pieces are not independent decorations. Their relations determine which paths close, which modes are compatible, and which local behaviors can become global. At Los Alamos, symmetry was engineered so distributed physical actions could converge toward one central event. In the Zeta-Space program, symmetry is proposed as the mechanism by which distributed local spectral data become one global analytic object. Conlocal modes gather into a theta function. Reciprocity carries them to windings on the seam graph. And a Mellin transform assembles the completed zeta function, lambda of S. One geometry attempted to compress matter. The other attempts to compress arithmetic information. In both stories, the center is not simply a location. It is the place where many independent structures are forced to agree. On July 16, 1945, the implosion design was tested at Trinity. The geometry worked. Less than a month later, atomic bombs were used against Hiroshima and Nagasaki. The solution to an extraordinary scientific problem became the destruction of cities and the beginning of the nuclear age. This is why the story cannot end with admiration for symmetry. Mathematics can describe convergence. It cannot decide what deserves to be placed at the center. A beautiful construction can solve the problem it was given, while revealing nothing about whether that problem should have been pursued. The Greenglass drawing also offers a warning for any ambitious mathematical program. A picture may contain genuine insight without containing a proof. It may preserve the shadow of a structure while omitting the machinery that makes the structure work. Zeta space must therefore travel in the opposite direction from wartime secrecy. Its objects must be publicly defined. Its symmetry actions must be explicit. Its operators must be constructed. Its spectral claims must survive independent verification. The lesson to inherit from Los Alamos is not secrecy, destruction, or mythologized genius. It is the relentless passage from sketch to model, from model to test, and from failure to correction. The first image shows geometry remembered imperfectly, after it had changed history. The second shows geometry reaching toward a mathematical future that has not yet been established. Between them lies the responsibility of rigor, because the center is not where the story ends. The center is where everything must agree.